Here you see a very classical example. Whatever when you look at whatever that describes the central limit theorem, this is one of the first examples that is given. Assume that we have uniformly distributed independent random variables in the interval 0 to 1 exabytes, okay, and we define the sum of n or k such random variables as y sub k. Okay, so x sub i's are IID. And here we see this first one is the PDF of x sub I, any one of them. It's uniform between 0 and 1. And when you take just two of them, add them up, and you obtain y sub 2. And the PDF of y sub 2 is this green line here, green graph. As you see, it's between 0 and 2, obviously, because the sum of two uniform random variables in 0, 1 can take values between 0 and 2. And you can obtain this by convolving this orange PDF by itself. And then when you add another one, so you obtain y sub 3. The PDF is this brown curve. And when you look at y sub 4, you add a fourth one. This is the red curve, the PDF. Okay. And what is the black curve? The black curve is a Gaussian distribution with a mean of 2 and variance of 4 divided by 12. Because if you remember, the expected value of this distribution, uniform from 0 to 1, is obviously 1/2. So when you add 4 of them up, the mean will be 2, 4 times 1/2. And the variance, if you remember, of a uniform distribution between 0 and 1 is 1/12. So when you add 4 of them up, which are independent, the variance will be 4/12. So as you see, even with a low number of random variables, as low as 4, you get a distribution which is really close to a Gaussian. So if you increase the number of random variables in the sum, for instance, you can do this yourself using any computation tool, and you will arrive at a curve that is extremely close to Gaussians, okay? The message here is with as low as 4 random variables that are IID, add them up, you get a random variable which is very closely very closely resembles a Gaussian. Well, obviously the Gaussian has support on the entire real line. The sum here has only support from 0 to 4. But we know that the probabilities outside this region is extremely small. So that doesn't really make much of an error. Okay, so what you see here is the central limit theorem is quite accurate as long as you have the conditions satisfied. The added random variables are IID and their variances are finite. Here's an example. The number of data packets arriving at an IP router is modeled as a Poisson random variable with a mean of 20 packets per second. Okay, what is the probability that at least 1250 packets are received in 1 minute? So we have the period of 1 second in which we know the mean number of arrivals is 20. Okay, so when you look at a longer period of 1 minute, okay, obviously each second you have a Poisson distribution of packets. So for the 1 minute, you can add them up. You are adding 60 Poisson random variables. In fact, we know from the independence nature of Poisson random variable, it stretches out. So when you add 6 IID Poisson random variables or 60 independent IID random variables, Poisson random variables, you still get a Poisson random variable. So in this question, we actually know the distribution, but again, you can approximate it or model it as a Gaussian. So we have here a Poisson distribution where the mean in 1 second is 20, the mean in 1 minute is 1200. Okay, so one thing you can do is use the Poisson random variable, but you see, numerically speaking, computation of such probabilities is not really easy because you have, for instance, 1200 to the power k, which is quite a large number for sufficient k, especially when you have k values greater than 1250. But on the other hand, you also have e to the power minus 1200, which is extremely small. So you are multiplying a very large number with a very small number, which is always problematic. And on top of that, you also have factorials. Okay, so it's not easy to compute. Well, MATLAB has a built-in function we will see here, but still, it's tedious. Alternatively, what you can do is approximate this as a Gaussian. Okay, we know the mean to be 1200. We also know that the variance of a Poisson random variable is equal to its mean in value. So the variance is also 1200. Okay, therefore, we can approximate the sum, the total number of packets in 1 minute, as a Gaussian with a mean of 1200 and the variance of 1200. And therefore, I can write this probability using a Q function, right? T exceeding 1250. So apply Q function to 1250 minus the mean, divide by the standard deviation. So you can be able to use the Q function. This is the result you get. And in fact, a little trick here, since the Poisson random variable is discrete, in fact, its probabilities are something like this. So when you use a Gaussian curve to approximate this, like something like this, obviously for each point here, you would have an interval. Okay, so usually if this is k, this here would be k plus 1 half, and this here will be k minus 1 half. Okay, the area under the Gaussian curve in this interval will represent the probability that the original discrete distribution equals k. Okay, so here what we are doing is t exceeding 1250, in fact, translates to, in the Gaussian distribution, if this is 1250, so if you have a probability here, and these are here, so I have a Gaussian curve like this, and to include 1250, I shall start my integration from not 1250, but 1249.5 to include this lower limit. Okay, so use that here, 1249.5, standardize it. This is what you get. Okay, let me raise this part a little bit. Okay, and as I said, we have the Poisson distribution in MATLAB. I also compared the value produced by that, which is 0.077214. And this is the result you obtain with a Gaussian approximation, 0.0765. It's quite close. And as you see, this trick here gives you a more accurate result than this one using 1250.